Hello students, good morning. Last session we discussed variation of molar conductivity of strong electrolyte. In that Debye-Huckel-Onsager equation we seen. So there a graph versus lambda m naught versus concentration raised to half. That graph we get a straight line. So on that we are find out the limiting molar conductivity. For strong electrolyte, if we increase concentration, the value is constant when we get straight line. Okay, we get if we increase 2 times concentration or 3 times concentration, conductivity increases, so we get a regular pattern, right? But when we are taking a weak electrolyte, in case of weak electrolyte, the graph is not plotted in this in that manner. Okay, so why? Because we know that weak electrolyte not completely dissociates, so variation is very large in that weak electrolyte. So for weak electrolyte, so we are not getting a regular pattern. So now we are going to take a variation of molar conductivity of weak electrolyte with concentration. Today we discuss variation of molar conductivity of weak electrolyte with concentration. So as I said, weak electrolyte not completely dissociate. Therefore, variations are going to be very large. So when we plot graph versus lambda m versus square root under concentration, that is like this. So when we plot the graph versus lambda m square root under c, so we are getting graph like this. So have seen that a graph come something like this. Okay, so all here also concentration increases. Here we are increasing a concentration, so molar conductivity, what happens here, decreases. On this place the molar conductivity is very high. When we moving, the concentration increases, the molar conductivity decreases. Have you seen this graph? So here so because of this, we are not getting a regular pattern like a straight line. In strong electrolyte, we are getting a straight line, but for not completely dissociation in weak electrolyte, yeah, we are getting graph like this. So variation more here. So you can see here variation more in this manner. When we increases, it is going to be less. Conductivity will be less. So when this graph we do extra plotting, here we are doing extra plotting, here also we are increasing, but they not reach this point. Okay, so it doesn't touch this zero concentration. So graphically molar conductivity of weak electrolyte, explaining or measuring limiting molar conductivity from this graph is not possible. So for that another method is there, that is there was a scientist whose name was Kohlrausch. He gave his law. Let's study the Kohlrausch law. So important questions come from this part, that is what is Kohlrausch law. So we'll study Kohlrausch law. Kohlrausch, he was a scientist. He seen very interesting pattern in many ions. He saw, suppose if we keep cation same and anion separate, in that case a difference in conductivity between two kind of ions is similar ions, that was recorded to be same. So we'll see, for example, if we take a limiting molar conductivity of KCl, So this is recorded at as a 149.9 Siemens centimeter square per mole. Like that, we are taking another one, that is limiting molar of NaCl, that we are getting a 126.5. So when we take a difference of this, we will get a 23.4. This is what cation, this is anion KCl, here cation, this is anion NaCl. So both in this case cation is different. Okay, here K is there, here Na is there. So cation is same but anions are same. So we looking at difference is 23.4. What he did, he changed this anion but cation remain same. Let's take another example, that is KNO3. KNO3 we get recorded as a 149 Siemens centimeter per mole. Here what he did, K is same but only is changing the anion. Similar another example, NaNO3. So here he kept K and Na as it is, but he only replacing the anion. So NaNO3 is 123. When we take a difference, he get a 23.4. Another way he did, like he took another example, that is KBr. Here also he is changing the anion. Instead of taking NO3, he taking a Br here. He got 151.9, and NaBr he got 128.5. So here anions, cations are he kept same, only changing the anions, but difference he get the same everywhere. So like that he recorded so many ions. You can see over here cations same, difference is 23, anions same, difference is 23 here, and here also difference is 23 you are seeing. So depending upon these kind of observation, he did so many experiment on this in this way. On that he gave one law that is known as a Colruyt law. Colruyt law. According to Colruyt law of independent migration of ions, this is a law limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and the cation of the electrolyte. This is very important for 1 mark. 1 mark question, 2 mark. This is one question we come from this Colruyt law. The law said that limiting molar conductivity of an electrolyte can be represented as the sum of individual contribution of the anions and cation of the electrolyte. So we can see here, KCl and NaCl, KNO3 and NaNO3, and KBr and NaBr. So here potassium and sodium giving same contribution, they are not associated with this chlorine. Okay. Similarly here also potassium and sodium define contributing giving. Depending upon this, he said what? We can take a strong electrolyte or weak electrolyte. Lambda m value is contributing. For example, another example we'll take. For example, value of lambda naught NaCl, we have to calculate the molar conductivity, that is lambda naught molar conductivity. For NaCl, both Na and Cl contributing total molar conductivity. This is going to be equal to what? Lambda Na plus molar conductivity of Cl minus, lambda Cl minus. Similar manner, if you taking KCl, that is what? Lambda K plus lambda Cl minus. Similarly, lambda MgCl2 means what? Lambda Mg2 plus here we are taking 2 lambda Cl minus. Why we are taking 2 lambda Cl minus? Because here 2 chloride ions which are present, so that's why we are taking 2 lambda Cl minus. So molar conductivity we can calculate like this. Okay. Also molar conductivity of weak electrolyte, we can take a weak electrolyte here. So we can take weak electrolyte, that as example. What example we are taking? That is acetic acid, CH3COH. This is a weak electrolyte. So here also it is contributing like this, CH3COO minus plus H plus, like this. This weak electrolyte will be contributing. So this here acetic acid contributing like this. Okay, I hope it clear for you. This is what Kohlrausch law. Next we go. So before going application, this Kohlrausch law, like this we are solving some example problems based on this. You will understand that. So next we are going to applications of Kohlrausch law. So what are the application? Let's see one by one. Applications of Kohlrausch law. Applications of Kohlrausch law. First, it helps to calculate molar conductivity of weak electron. What do you mean by molar conductivity of weak electrolyte? So example, we have calculate molar conductivity of weak electrolyte, that is what? Acetic acid, isn't it? How we have to calculate the acetic acid molar conductivity? It can be calculated by taking the molar conductivity of strong electrolyte. It is a weak electrolyte. By using strong electrolyte, we have to calculate the molar conductivity of this. So strong electrolyte molar conductivity calculate by we are did by Dubé-Huckel-Onsager equation, isn't it? So like that, this CH3CO, that is this acetic acid calculated here, that is this one will become CH3CO minus H plus ions, isn't it? Lambda CH3CO minus plus H plus ions. Okay, both these ion molar conductivity calculated by what? Strong electrolyte. So for this we can calculate it by strong electrolytes. So here we are taking a strong electrolyte, that is CH3COO Na. This one is a strong electrolyte. So this strong electrolyte, when we distribute, what happens? This becomes CH3CO minus plus Na plus. So according to Kohlrausch law, this is equal to CH3CO minus plus lambda Na plus. Okay, like this we have to take lambda NaCl here. Next we are taking lambda NaCl. This will strong electrolyte, so that is going to contribute like Na plus plus Cl minus, isn't it? Like that we are taking HCl. It is also H plus plus Cl minus. This is second equation. This is third equation. From this data we can take a value of CH3COOH. So that is how we have to take the value of CH3COOH. We only need what? CH3COO minus and H plus ions. No need to, we don't want Na plus K plus, Na plus Cl minus. We don't want the value. Only we want the value of CH3COO minus and H plus value. So for that, from these data, we have to include uncommon ions equation. Uncommon ion equation. What do you mean by uncommon ion equation? That we have to add uncommon ions. Let's see. Here for this first equation, this is first equation, this is CH3CO minus and Na plus. First equation and second equation. So here what is the common here? Na is common. Here also Na is common. So we don't take this equation. Let's see first and third equation. CH3CO minus Na plus. Here also H plus and Cl minus. There is no common in this ion. So let's add 1 and 3. So for let's see. So for first and third equation, there is no common ion. So first equation and third equation, we are adding common ion equation. We need to, what happens, we'll write the first and third equation. I will write here. CH3COO minus, we are adding this one, lambda Na plus. Next, third one, we are adding H plus plus Cl minus. These are, first we have to add uncommon ions. So one and equation 3, we don't have a common ions. That's why you are adding here. Next, common ions we have to subtract. Here we having a common ions equation 2, that we have to subtract. That is Na plus plus Na plus minus Cl minus. We have to subtract common ions. First we have to add uncommon ions, that is equation 1 and 3. Here there is no common ions. So first we have to, equation 1 and equation 3 we have to add. Next, equation 2 we are having a common ions, that we have to subtract. So like that we are getting Na and Na cancels, Cl and Cl cancels. Remaining what? That is CH3COO minus plus H plus. So we are getting CH3CO minus and H plus. That is what we are having a desired product. So you are clear that. So we'll do problems like this. Uncommon ions adding and common ion subtracting. We are getting a molar conductivity of desired electrolyte. So Kohlrausch law help us to for this. This is first application. Next, move on to second application. Second, help us to calculate degree of dissociation of weak electrolyte. Degree of dissociation of weak electrolyte is given by what? Alpha. Alpha is degree of dissociation. So alpha, that is going to be going to be equal to what? That is lambda raised to C divided by lambda naught. This is alpha, that is dissociation, degree of dissociation. This is equal to lambda raised to C divided by lambda naught, where here lambda C is what? Molar conductivity of any concentration. Lambda C what? Molar conductivity of any concentration. By this lambda C we have to calculate what? Lambda C is equal to K into 1000 divided by M. Isn't it? So if they not given lambda C value, in problem if they not given lambda C value, so we have to calculate it by using this formula. So like that, lambda M naught, limiting molar conductivity, lambda M naught. So that is limiting molar conductivity. We have to calculate like first application. First application we are calculating lambda M naught by taking, for example, taking AB electrolyte, so we can write lambda A plus plus lambda B minus. So from this first application we are calculating lambda naught of weak electrolyte. So we are getting lambda C from this equation, from this formula, and lambda naught. By doing like this we are getting both the values, and then we apply and we are getting a alpha. So we'll get the degree of dissociation value. Understood? Second application. Next move on to third application, that is to calculate the value of K. K is what? Which is dissociation constant. So dissociation constant, that is going to be equal to what? K equal to C alpha square divided by 1 minus alpha is the formula. So for this alpha value calculated from application 2, we are did in our application here. From this we are getting a value of alpha, so that you have to put in this alpha value, and then C, that is concentrated, they will given that. So from this, putting the alpha and concentration value, we are getting a value of K. So this is third application. Next, last one, that is fourth application, that is to calculate the solubility of sparingly soluble salts. So to calculate the solubility of sparingly soluble salt, so solubility we can calculate it by the formula what? Lambda naught equal to K into 1000 divided by M. It is also written it as a lambda naught is equal to K into 1000 divided by solubility. For this we have to calculate the solubility. So here we have to calculate solubility. What happened? The solubility is equal to what? Then solubility is equal to K into 1000 divided by lambda naught. Okay. So here we get K value is getting from application third, and lambda naught is getting the value from application 2. We are calculating the application 1. From that we are getting the value, and K value will get we have got, and lambda naught value we have got. So from this we have to put the value of all this. We are getting a solubility. Have you got the point? Lambda naught means what? Molar conductivity. So calculated how? Like this, lambda naught, that is lambda A plus plus lambda B minus, by this method. And this is what? K, the value of K we are getting from this. K is equal to C alpha square divided by 1 minus alpha. All this value you are getting. So those all is you have put in this formula. We are getting a solubility. So these are the Kohlrausch law applications. Thank you.